Welcome to Electrical Circuit Analysis. Throughout this tutorial, I'd like to request you to pause the video whenever you need it and keep pen and paper with you so that we can solve problems to consolidate our understanding. In this tutorial, we're going to talk about Kirchhoff's current law, Kirchhoff's voltage law, circuit validity assessment, and voltage and current divider. In the earlier lecture, we talked about Ohm's law, but Ohm's law by itself is not sufficient to analyze large circuits. So what we do to analyze relatively larger networks, we couple Ohm's law with the Kirchhoff's two laws so that we can analyze a large variety of electrical circuits. The Kirchhoff's two laws are Kirchhoff's current law and Kirchhoff's voltage law. So Kirchhoff's current law, KCL, states that the algebraic sum of currents entering a node is 0. So this means that, for instance, here we have a node, and it has got 1, 2, 3, 4, 5 branches, and each of the branches has a current. So current I1 is entering the node, current I5 is leaving the node, current I4 is entering the node, and so on. So Kirchhoff's current law basically states that if we sum all the currents that are entering the node, and if we also sum all the currents that is leaving the node, we'll find that both of the currents are equal. So that is the main idea of KCL. So here the current entering the node are I1, I3, and I4, and the current leaving the node are I2 and I5, which means I1 plus I3 plus I4 is equal to I2 plus I5. So the current entering the node is equal to the current leaving the node, and this makes total sense because the node obviously cannot capture charge or cannot store energy. Now there is an alternative and a probably easier way to apply KCL. So what we're going to do here to apply KCL, we'll assume that all the currents are either entering the node or leaving the node. I personally assume that all the currents are leaving the node. So if the current is actually leaving the node, we will give the current magnitude of that branch positive, and if the current is actually entering the node, the sign of the current will be negative, because as we saw in an earlier lecture that current I going into the node is equivalent to current minus I going out of the node. So let me illustrate this with an example. So in this circuit, for instance, we have three nodes, A, B, and C, and if we're trying to apply KCL at node A has 3 branches we observe. This 4 ampere branch, this I1 branch, and this 3 ampere branch. So if we're trying to apply KCL at node A, we see that the 4 ampere current is leaving the node A, which means we give plus 4, because we're assuming that all the currents are leaving the node. And in this branch we see that the current I1 is actually entering the node. So if I1 is entering the node, that means minus I1 is leaving the node. That is why we give minus I1 in the equation. And the current in the 3 ampere branch here, the current is actually leaving the node A, which is why it's plus 3. And then we write equals 0. From this equation, we can get the unknown branch current I1 here. So I think you now understood what I meant, that we're assuming here that all currents are leaving the node, and if the current is actually leaving, we give a plus sign in front of the magnitude of the current, and if it's actually entering the node, we give a minus sign in front of the magnitude of the current, because for instance here, I1 going into the node A is actually equivalent to saying minus I1 is going out of node A. So let's apply KCL at node C here again. Node C has 3 branches here. There's 3 ampere branch, this I2 branch, and minus 2 ampere branch. So we can see that the minus 2 ampere current is actually leaving the node C, which means we don't change its sign, we just leave it as it is, minus 2. Okay, I2 is entering the node C, which means minus I2 is leaving the node. So the outgoing current in this branch will be minus I2, so we just write minus I2 here. Again, 3 ampere is going into the node C, which means minus 3 ampere must be leaving the node C. So we write minus 3 here, and we equate all this equal to 0. Note that the number of branches connected to the node is equal to the number of terms in the KCL. For instance, here for node C, you have 3 branches connected to the node C. This one, and this one. You have one term corresponding to each of the branch on the left-hand side of the KCL. So this is also another point to note. So you can apply KCL either way, like you can assume that current entering node is equal to current leaving node, or you can also assume that current is always leaving the node, and if the current is actually leaving the node, you keep the sign positive or unchanged, and if the current is actually entering the node, you reverse the sign. That is, if it's minus, you make it plus, or if it's plus, you make it minus. So hopefully you have a clear idea how to apply KCL. Now I'd like to request you to pause this video and try to apply KCL at node B, and then we'll try to match our answers. So please pause this video. Okay, so hopefully you've been able to apply KCL at node B. So equation at KCL at node B will be minus 4 plus I1 plus I2 plus 2 equals to 0. Kirchhoff's second law that we're going to discuss is Kirchhoff's voltage law, or KVL, which states that the algebraic sum of all the voltages around a closed path or loop in a circuit is 0. So what does this mean? This means that if you start at a particular point in a circuit and go around the loop, it could be clockwise, it could be anti-clockwise, and you keep summing the voltages as you go along, so the sum of voltage drops will equal sum of voltage rises. So let me show KVL with an example. So for instance, let's say in this circuit we go counterclockwise, and we start from here, and as we go counterclockwise, we'll just sum the voltage drops, and we'll just note the voltage drops, and then we'll note the voltage rises, and we'll just sum them and just equate them like this. So as we go from bottom to top here, we go from lower potential to higher potential. How do we know that? This is the positive terminal, this is the negative terminal. So as we saw in lecture 1, that this means that the voltage of this point is V1 high with respect to this point. So here basically we're having a voltage rise. So we just note here V1 voltage rise, and if we assume this is plus and this is minus, this polarity of this resistor, as we go anti-clockwise, we go from higher potential to lower potential, which is why V2 is a voltage drop. So that's why we write V2 here. Again, as we go from the positive terminal to the negative terminal of V3, we go from higher potential to lower potential, and that's why this is a voltage drop, and that's why we write V3 on the side of voltage drop. Now, as we go clockwise across this voltage source V4, we go from lower potential to higher potential, and that means this is a voltage rise, which means V4 is basically a voltage rise, which is why we write V4 on the right side, which is the side of voltage rise. Again, this unknown circuit element has a voltage drop of V5 as we go from right to left, that is anti-clockwise. So we write V5 in the side of voltage drop. Now we just add plus signs here in between these variables, and there you go, you have your KVL equation. So just to remind you again, how did I determine which one is voltage drop and which one is voltage rise? I just looked into the polarity signs and decided whether or not I'm going from lower potential to higher potential or higher potential to lower potential. If I'm going from lower potential to higher potential, this is a voltage rise, and if I'm going from higher potential to lower potential, this is a voltage drop. So sum of all voltage drops is equal to sum of all voltage rises. Now there is an alternative way to apply KVL that I'd recommend you to follow. So this is actually a much easier way, in my opinion. So what you do here is that to apply KVL, again, you assume clockwise or anti-clockwise direction around the loop. And you sum the voltages such that the voltage drops are positive and rises are negative. So here we don't write the voltages on two sides of the equation. We write them on one side, just like we did for KVL, assuming that the voltage drops are positive. Remember what we just did for KCL? We assumed that the current going out of the node is positive and current coming inward is negative. We're doing the exact same thing. Here we're assuming that the voltage drops are positive and the rises are negative. So again, as we go anti-clockwise from this point, across V1 we go from lower potential to higher potential. So this is a voltage rise. But we're assuming the voltage drops are positive, which is why we're giving a minus V1. In other words, V1 rise is equivalent to saying minus V1 drop. So that's why we write minus V1 here. Again, for V2 here, we're going from higher potential to lower potential. So this is a voltage drop, so we don't have to worry about the sign, it's plus V2. Again, as we go through the resistor, we're going from higher potential to lower potential, and this is a voltage drop, and since it's a voltage drop, we didn't have to worry about the sign, we just write plus V3. And through this voltage source, as we go anti-clockwise, we go from lower potential to higher potential, which means we are basically, V4 is basically a voltage rise, but since we're assuming that the voltage drops are positive and rises are negative, we write minus V4. And again, as we go anti-clockwise through this V5 voltage, we're going from higher potential to lower potential. So V5 is basically a voltage drop, and we're assuming voltage drops are positive, so we write plus V5. And we set this equal to 0. Again, similar to KCL, note that the number of terms in the KVL equation is equal to the number of circuit elements. So personally, I always go clockwise, and I always assume that voltage drops are positive. So I'd like to suggest you to follow one convention for all of your problems so that you don't mix up. So for KCL, I assumed that current is going out of the node. So current going out of the node is positive current, and current coming into the node is negative. Here for KVL, I'm assuming that voltage drops are positive and voltage rises are negative, and we write all the voltage drops and rises on one side of the equation. Now rearranging this equation gives us the original equation. So voltage rises equal voltage drops, just like we derived or showed one slide back. So it's basically the same thing. Okay, now we're going to apply KVL to solve the problem. So we're going to find this voltage V1 and V2 in the circuit. So to determine V1 and V2, we'll apply Ohm's law and Kirchhoff's voltage law. So let us assume that the current I flows through the loop as shown in the figure on the right, and the current I flows in the clockwise direction. So if I apply Ohm's law here, we know V1 is equals to 2I1 and V2 is equals to minus 3i. Now you might wonder why there's a minus sign here and why not a minus sign here. So here across a resistor, current always goes from higher potential to lower potential. So okay, so why do we have a minus sign in front of the equation of V2? So why V2 equals to minus 3i? So the reason is that when we're computing the voltage across the resistor here, we are always assuming that current is going from higher potential to lower potential, which means this point for this resistor will be plus and this point will be minus. Similarly, for this 3 ohm resistor here, this point will be plus and this point will be minus. If it was plus here and minus here, V2 would have been plus 3i. Now that the polarity is the opposite, that is, current is going from lower potential to higher potential, we need a minus sign to sort of invert this polarity. So another way to do this is that you can define another variable called, let's say, V3, whose polarity is, which is the same voltage, basically the voltage across the 3 ohm resistor, but the polarity will be plus here and minus here. Then V3 will be equals to plus 3i, and V2 will be equals to minus V3, because as we know, if we have to invert the polarity of a voltage, we need to sort of reverse the sign of the value of, or the magnitude of the voltage. So that's why we're giving a minus here, because current is going clockwise, which means top to bottom across this 3 ohm resistor, which means this is the higher potential, this is the lower potential, but the potential, the polarity of V2 defined here is the opposite of what it should be, which is why we're giving a minus sign to sort of compensate for this fact. Now if we sort of apply KVL here, we get minus 20 plus V1 minus V2 equals to 0, and then if we just replace the values of V1 and V2 from these two equations to here, we get V1 and V2. So hopefully you have a clear idea how to apply KVL here. So please pause this video and try to solve this problem using KVL. Okay, so hopefully you've been able to solve this. So the KVL equation will be, if we assume a clockwise current I in the circuit, the equation of KVL will be minus 10 plus 4i minus 8 plus 2i equals to 0, and V1 will be 4i and V2 will be minus 2i. Okay, now we're going to see an application of KVL. So KVL basically allows us to combine multiple voltage sources and replace them with one voltage source. So when voltage sources are connected in series, KVL can be applied to replace them with one voltage source in figure B here. So here we have 3 voltage sources in series, V1, V2 and V3. So these 3 voltage sources can be replaced with one voltage source Vs, whose voltage is V1 plus V2 minus V3. So how do we get this? So if we just take the KVL in this loop here, minus VAB plus V1 plus V2 minus V3 equals to 0, and if we change sides, you get the equation. You end up with this equation. Now remember, I said a few slides earlier that you can apply KVL even if there is an open circuit. You know, there is an open circuit here, and I'm still considering it as a loop, and I'm still applying KVL. Okay. So you can combine voltage sources only if they're connected in series. You cannot combine this way if they're connected in parallel. Furthermore, to avoid violating KVL, a circuit cannot contain 2 different voltage sources, V1 and V2, connected in parallel, unless both of the voltages are equal. So here's an example. Here between the terminals A and B, I have 2 independent voltage sources, one of 10 volt and the other of 20 volt. You can see this is an invalid connection, because you cannot connect to, you can only connect multiple voltage sources in parallel if they have the exact same values, but they don't have the exact same values, which is why this circuit is an invalid circuit, or this connection is an invalid connection. So to further convince you, I'd like to ask, what is the voltage value VAB? Is it 10 volt or 20 volt? Now remember that in a resistive network, the current through a branch, or the voltage across the terminal, is always constant in a resistive network. So VAB here cannot have two values, like 10 and 20 both at the same time. So we understand from this that this is not a valid connection. If that doesn't convince you, just take KVL in this loop. So minus 10 plus 20 equals to 0. So the left hand side does not equal the right hand side, which means this circuit violates KVL, which means this circuit is an invalid circuit. Just like we can combine several voltage sources in series and replace them with one voltage source, we can also combine several current sources in parallel and replace them with one current source. So here I have three current sources in series, I1, I2, and I3, and if I can combine these three current sources and replace them with one current source, where the value is just the algebraic sum of the current sources, of the individual current sources. So how do I get this? IT equals I1 minus I2 plus IT. How do I get this equation? So if you take KCL at node A, you get I2 plus IT plus I2 equals to I1 plus I3. If you just switch sides, you end up with this equation. So when current sources are connected in parallel, KCL can be applied to combine the current sources and replace them with one current source. Now you can only combine current sources if they're connected in parallel. You cannot combine current sources in this manner if current sources are connected in series. In fact, a circuit cannot contain two different current sources, I1 and I2, in series unless both of them are equal. Otherwise, KCL will be violated. So for instance, we have an example circuit here. Here this 5 ampere and 10 ampere current sources are in series. So both of the values of the current sources are not equal, which means this is an invalid connection. To further convince you that this is an invalid connection, I'd like to ask, what is the loop current? Is this 5 ampere or 10 ampere? So the loop current, or this mesh current, should be unique, but it's not unique here, which means this is an invalid connection. A further proof of this is that if we apply KCL at node A here, we see that 5 ampere current is coming and 10 ampere current is leaving, which means the left hand side does not equal the right hand side, which means the circuit violates KCL. That means the circuit is in fact an invalid circuit. So when we're trying to assess the validity of a connection, we need to see whether or not we can find voltage sources in parallel and/or current sources in series. So if we don't find these two suspicious combinations, we can say that the circuit is valid. If you find one voltage source in one example of two or more voltage sources in parallel, or two or more current sources in series, we need to look into them and see if the magnitude or values of those sources are identical. If they're identical, then we'll say that the circuit is valid. If they're not identical, we'll say that the circuit is invalid. Now we're going to see some example of this, how to assess the validity of an electrical circuit using these principles. But before that, I'd like to just summarize KVL and KCL. So KVL is applied across a loop, but KCL is applied at a node. And to apply KCL, we'll assume that all the currents are actually leaving the node. So if the current is actually leaving the node, the sign will be positive, and if the current is actually entering the node, the sign will be negative, because current I going in to a particular node is equivalent to saying that minus I is going out. Then we set the equation equals to 0. To apply KVL, we'll assume voltage drops are positive, and then we assume clockwise current direction around the loop, and we'll sum the voltages such that the voltage drops are positive and the rises are negative, and then we'll set the equations equal to 0. You can also apply KVL if your loop contains an open circuit. So just to summarize, when voltage sources are connected in series, KVL can be applied to replace them with one voltage source, but if they're connected in parallel, it can only be a valid circuit when all of the voltage sources have equal values, have identical values. Similarly, when current sources are connected in parallel, KCL can be applied to combine the current sources and replace them with one current source. However, when current sources are in series, the circuit is invalid except when all the current sources have identical values. Then the circuit is valid. Okay, now please pause the video and write down in your scrap paper or notebook which circuit is valid and which circuit is not, and then we will match our answers. So please pause this video. Okay, so hopefully you have come to a decision or conclusion. So in figure A here, we have two voltage sources in parallel. Okay, that triggers our internal alarm clock, if you will, because I said if two voltage sources are in two or more voltage sources are in parallel, or two or more current sources are in series, we suspect that there is a problem in the circuit. However, these two voltage sources have identical values, which is fine, which does not violate KVL. So the circuit in figure A is a valid circuit. Similarly, the circuit in figure B, so the circuit in figure B also does not violate KVL, because at node A you have 5 ampere current coming and 5 ampere current leaving. Okay, the circuit in figure C actually violates KVL, because, well, first of all, we're looking at the circuit in figure C, and we see that two voltage sources are in parallel. Okay, so then we suspect this thing, and then we sort of look into the values of the voltage source. One is 10 volt and another one is 5 volt. Then we say that, okay, this is not a valid connection. To further confirm this, you can take a KVL and see minus 10 plus 5 equals to 0. That's an invalid equation, which means the circuit is invalid. Similarly, this is also an invalid circuit, because here you have two current sources in series and the values of them are unequal. To further confirm that, we take KCL at node A and we see that 5 ampere current is coming and 2 ampere current is leaving, which is not possible. Okay, now please pause this video and write down your answers, and then we'll match our answers. Okay, so please pause the video. Okay, so hopefully you have come to your decisions or answers. So in figure A, VAB here, this voltage source gives 5 volt and this voltage source gives 15 volt, because Vx is 15 here, so 3 times 5 is 15. So with two voltage sources in parallel giving different voltages, which means this is an invalid circuit. In figure B, it does not violate, we don't suspect this circuit because we don't have two voltage sources in parallel or two or more current sources in series, so this circuit is fine. So is figure C. Figure C is also a valid circuit, but in figure D you have two current sources in series, and one is giving 2 ampere, another one is giving 6 ampere, and if that doesn't convince you, just take KCL at node A. You see that 2 ampere current is coming to node A and 6 ampere current is coming to node A, and no current is leaving, which means this KCL at node A basically results in an invalid equation, which means that the circuit in figure D is also invalid. Now please pause this video and try to solve this problem, and then we'll match our answers. Okay, so hopefully you solved the problem. So the answer to this question is this. Here, if you just take KCL at this node, you have alpha Vx plus 15 equals to 0, and Vx is basically minus 25, because the polarity of Vx is defined as positive on top and negative at the bottom, but the polarity of this voltage source is negative on top and positive on bottom. If you can invert the polarity of this voltage source, you can make it plus and make the bottom minus, provided that you change the sign. That is, it becomes minus 25 volt, and then the polarity of this voltage source matches with the polarity of this variable, which is Vx becomes equals to minus 25. Now if you put Vx equals to minus 25 in the KCL at this node where my cursor is, you get the equation, you get the value of alpha. So yep, so that's it. Okay, now we're going to see an interesting application of KVL called voltage divider. So this is a voltage divider circuit basically, where you know across the terminal AB you have two resistors in series, R1 and R2, and you know the voltage of the terminal AB. Somehow here you have a voltage source V, which means VAB is equals to V here, but it doesn't mean there has to be a voltage source. I mean, if you just know the voltage of this terminal A and B, and you have two resistors in series, then you can apply the voltage divider rule. So if you take KVL in this loop and solve it, you get I equals to V by R1 plus R2, and then you apply Ohm's law to obtain V1 and V2. So V1 is R1 by R1 plus R2 times V, and V2 is R2 by R1 plus R2 times V. So if two resistors are in series, the voltage across each of them, V1 and V2, depends on its own resistor divided by its own resistor divided by the other resistor times the voltage of the terminal. So now if R1 is way larger than R2, then the voltage drop across R1 will also be larger than R2. The voltage divider is thus used to reduce a voltage value to a desired level. So we can also apply the voltage divider formula here, this one and this one, to perform circuit analysis. So if we just remember this is V1 equals to R1 by R1 plus R2 times V, and V2 equals to R2 by R1 plus R2 times V. You don't have to take KVL and apply Ohm's law each time. So yeah, so that's the advantage of voltage divider. And also voltage divider is used to reduce a voltage to a certain level. Okay, so I'm going to use voltage divider to solve this problem. So in this circuit, in figure A, we need to determine V0 and I0. So to apply V0 here, we can combine these two resistors. These two resistors are in parallel. So the equivalent, we can replace them with one equivalent resistor, 3 times 6 divided by 3 plus 6, which is 2. And once we do that, we get the circuit in figure B, and then we have our usual voltage divider format, two resistors in series, and we know the terminal voltage 12 volt. Now V0 is equals to 2 by 2 plus 4 times 12. So that's V0. And once we get the V0, I0 is, we can just apply Ohm's law to get I0. I0 equals to V0 by 3. So to apply voltage divider, we need to have this specific format, the two resistors in series, and you know the voltage across the terminal. So that's an application of voltage divider. Similar to voltage divider. Okay, so excuse me. So we also have a problem here. So please pause this video and try to solve this problem and using voltage divider, and then we'll match our answers. Okay, so hopefully you've been able to solve this problem. V1 is equals to 5, V2 equals to 10, and I1 and I2 is this. So what we can do is that we can combine these two resistors into one, and combine these two resistors into one. Then we have two resistors in series, and if we apply the voltage divider rule, we get V2 and V1, and then we can further apply Ohm's law to obtain I1 and I2 from this circuit. Okay, now we're going to see that if two resistors are in parallel, you can determine the current of each of the branches if you know the overall current that is going into the node. So let's say we have two resistors R1 and R2 in parallel, and the current through R1 is I1, and the current through R2 is I2, and the current that's entering here is I. So if we know I, R1 and R2, current divider tells us how to find I1 and I2. So I1 is equals to R2 by R1 plus R2 times I, and R2, and current in this branch is, in the R2 branch is I2 goes to R1 by R1 plus R2 times I, which means when we're talking about the branch of R1, the current in the branch of this branch depends on the resistor of the other branch divided by the resistance of the other branch plus the resistor of the current branch times the overall current, and the exact same thing for this one. So you can compare the equations of voltage divider and current divider by contrast, that for voltage divider the voltage across the resistor depends on its own resistor value, which is why in the numerator you have the same resistor, but for current divider you have the other resistor divided by the other resistor plus this resistor times the overall current. Now if R1 is way greater than R2, I2 will be much higher than that of I1, and the current divider thus is used to reduce the current to desired level, similar to a voltage divider. And we can also perform circuit analysis by applying the current divider formulas. And just to remind that the current in one branch basically depends on the resistance of the other branch. So that's the easy way of remembering the current divider formula. Okay, so we'll now apply the current divider formula to compute the V0 resistor in the circuit. So please pause this video and try to resolve the problem yourself, and then I'll explain how we do this. So please pause this video. Okay, so here the 6 kilo and the 12 kilo resistors are in series. So if we combine them, we have our usual current divider format, two resistors in parallel in figure B here. So that's why I've just combined these two resistors, 12 and 6 in series, so it's 18 kilo. Now it's our usual current divider formula. Now we can determine the current in this branch, I1. So I1 is equal to 18 divided by 18 plus 9 times 30 milliampere, and that's 20 milliampere. And then we can just apply Ohm's law to get our desired voltage V0. Okay, now please pause this video again and try to solve this problem, and then we'll just match our answers using current divider, of course. Okay, so hopefully you've been able to get a clear idea of what voltage divider and current dividers are. So if you have any questions, please feel free to post them in the comment section. Thank you.